These are MCQs related to electric potential. How much work is required to carry a 6 microcoulomb charge from the negative to the positive terminal of a 9-volt battery? Okay, so the work done formula is Q times V. So Q is 6 into 10 power minus 6 coulomb times 9-volt battery. So 54 into 10 power minus 6 joules. C is the answer. The electric potential due to a point charge minus Q at a point at distance r from mid-center is, see here, electric potential formula is V equals 1 by 4 pi epsilon naught charge divided by the distance from the point. Here this charge, if it is negative, electric potential is also negative. So it should be this 1 by 4 pi epsilon naught can be written as k. So we can write minus kq divided by r. So this is the answer. This is actually D. The potential at a point due to a positive charge of 100 microcoulomb at a distance of 9 meter. Let us calculate it. So V equals 1 by 4 pi epsilon naught Q divided by R. So do not forget here electric potential is a scalar quantity and in the denominator R only will be there, not R squared. Now let's substitute the values. 9 into 10 power 9 for 1 by 4 pi epsilon naught. Q is 100 microcoulomb, so it is 10 power minus 6 divided by 9 meter. 9 will go away. We'll have 10 power 9 plus 2 minus 6. This will give you 10 power 5 volts. Answer is C. The electric potential at the surface of an atomic nucleus of radius 9 into 10 power minus 13 centimeter is given. So here electric potential we have to calculate, but for the charge, total charge is Z times E. Z is the atomic number times the charge. E or we can use Q also divided by R. So 1 by 4 pi epsilon naught is 9 into 10 power 9 times 50 times charge is 1.6 into 10 power minus 19 divided by R is 9 into 10 power minus 13. Since it is given as in centimeter, we have to convert into meter. So it is 10 power minus 2. So we'll have into 10 power 6 volts. So this is the answer. At a point A, there is an electric field of 500 volt per meter and potential difference 3000 volts. The distance between the point charge and A is, which means that there's a point charge and it creates electric field everywhere, and then we are standing here. This is at the point P. This point P is at R distance from the charge, and here at point P, E is given and V is given, and we have to find out what is the distance between these two. I mean the point P from the charge Q, which produces this electric field. So there's a relation between E and V. We can write this way. E is written as 1 by 4 pi epsilon naught, this source charge divided by R squared. This is the magnitude of electric field. And the electric potential can be written as 1 by 4 pi epsilon naught Q divided by R. So by comparing these equations, we can write E by V equals R. So we can calculate the distance, not E by V. I think it should be V divided by E. Is equal to R. So we can calculate R now 500, 3000 ohms. 3000 volts divided by electric field is 500. So we'll have a 6 meter. So A is the answer. Two-point charges plus microcoulomb and minus 10 microcoulomb are placed at points A and B. So plus microcoulomb, 10 microcoulomb minus 10 microcoulomb are placed at some points A and then point B. If P and Q are the points lying along the perpendicular bisector line. Okay, so how do we draw that? Like this is a line joining A and B, and then this is the perpendicular bisector. So let's draw this way. And there's a point, there are 2 points P and then Q, maybe somewhere up and down or maybe on the same side. The work done in taking a charge of a 5 microcoulomb from P to Q. So from P to Q, if you take a charge of 5 microcoulomb, what will be the work done? So we have to find out the work done. So first we have to remember that the dipole at the perpendicular bisector, the dipole has two charges plus q and minus q, equal and opposite cases, and the equatorial plane which goes through the bisector of this two charges, bisector of this dipole is actually equipotential surface. Equipotential surface. So which means that if you take the charges from any point, from one point to another point in the equipotential surface, since the potential is the same, work done is 0. So this should be B. The electric field and electric potential inside the charged spherical shell. Okay, so for a charged spherical shell, electric field inside is a 0. Outside there is some voltage. Okay, and inside also it should be the same. So E is equal to 0, but V is not equal to 0. The same here in terms of graphs. In the case of a charged metallic sphere, same thing, charged metallic sphere, the potential changes with respect to the distance. We have just learned that potential inside is a constant, and when you go out of the sphere, it will decrease as 1 over r. So it's like this is a sphere, and then inside it is a constant. Outside, when you go out, then it's going to actually decrease. So this is r. So B is the right answer. The potential at the center of the sphere, if hollow metallic sphere of radius 10 centimeter is charged, such that potential on the surface is 70 volts. Okay. So what we have to find out the electric potential at the center, but on the surface we know it is a 70 volts. So on the surface it is a 70 volts. We want to find out the what is the electric potential at this point, but we know everywhere inside it should be the same. So it is a 70 volts. The potential on the hollow sphere of radius 1 meter, okay, a hollow sphere of radius 1 meter is 1000 volts. 1000 volts. Then potential at 1 by 4 meter is somewhere here, okay, at this point P. Uh, from the center of the sphere, we have to find out. So we know potential everywhere inside, not only here, everywhere inside it should be the same. So it is 1000 volts. That's all. Thank you.